Problem is an innovative way of power generation involves utilization of geothermal energy. The energy of hot water that exists naturally underground is the geothermal energy as the heat source. If the supply of hot water at 140 degrees centigrade is discovered at a location where the environmental temperature is 20 degrees centigrade, you have to determine the maximum thermal efficiency of a geothermal power plant that can be built at this location. So you have to determine the maximum thermal efficiency, which is also the Carnot efficiency. And do you remember the formulation for this? Anybody remembers the formula for Carnot efficiency?
1 minus TL.
This is 1 minus TL upon TH. Can you find out the efficiency?
Yes, sir.
Please find it out and let me know.
Sir, 29%.
So I've got one answer as 29%. Anybody else has got a different answer?
Yes, sir, 29%.
29.
All right. So the issue that I wanted you to find it out, the reason being that you should remember that the temperatures in this efficiency formula are absolute temperatures. So don't take the ratio in centigrade, but convert it into kelvins for the absolute scale, and this would give you 1 minus 0.709. This would be essentially
0.29.
0.290, which is essentially 29%. Clear? All right. Now the next problem is, all right, you have the solution, so I'll erase all. So I have the solution for you. The next problem is that you have a Carnot refrigerator that operates in a room in which the temperature is 25 degrees centigrade. The refrigerator consumes 500 watt of power when operating and has a coefficient of performance of 4.5. You have to find out the rate of heat removal from the refrigerated space, and secondly the temperature of the refrigerated space. So I'll give you 2 minutes, I guess, if you could find it out, and then we'll look into the solution. All right, so quickly try to solve it, and then we'll look into the solution. In the meanwhile, let me draw the schematic for you so that you know what a refrigerator is. This is the refrigerator. Work in is being provided to this refrigerator. This refrigerator takes in the extracts the heat from a refrigerated space in the form of Q dot L, and it rejects the heat to a high temperature region, which is the atmosphere or your atmosphere outside the refrigerator, atmosphere at TH, and the rate at which it is throwing the heat is QH. So first find out the rate of heat removal from the refrigerated space.
Sir, the heat QL is 2250.
Q dot L is 2250 kilowatts or watts?
Watts, sir.
Watts. Good. And the second part, have you done the second part also?
No, sir, not yet.
Do you know how to do it?
I'm thinking, sir.
All right. Have 1 minute, try to think. and then we'll move on towards the solution. 1 minute.
Sir, temperature 383 Kelvin.
Temperature, all right, we have got one answer as 383 Kelvin. All right, let's see. Let's see. So the first part, sorry,
243 Kelvin.
29
I
degrees
am your voice is very distorted. I am not able to hear you.
minus
243.
29
Can
degrees
you type
centigrade.
minus 29 degrees centigrade? All right, let's see the correct answer. So the COP of a refrigerator is essentially Q dot L over work dot net in. You have to find out Q dot L. So Q dot L is essentially COP of refrigerator is 4.5 multiplied by work net in, which is 500 watts. This would give you 2250 watts. Now, if you know Q dot L, can you find out Q dot H? Q dot H is essentially work net in plus Q dot L, which is 500 watts plus 2250 watts, which is 2750 watts. Now, for a Carnot refrigerator, you know that Q dot L over Q dot H is essentially T dot L over T dot H. You have to find out the lower temperature TL, the temperature of the refrigerated space. So T dot, sorry, there is no dot on it. So TL over TH. So TL would essentially be Q dot L over Q dot H multiplied by TH, which is 2250 into TH is 25 plus 273 divided by 2750, which comes out to be
364.2.
sorry
364.2.
are you sure
243.8.
243.8 degrees centigrade, which is essentially minus 29.18 degrees Celsius. This is, sorry, 243.8. This is the absolute scale. This is Kelvin value, and this is in centigrade. Clear enough? Is the solution clear to you?
Yes, sir.
All right. All right. Now, moving on towards the last numerical that we'll be doing for this chapter. Again, I'll remove the. You have the solution for you. You can always refer back to the solution. Uh, Moving on to the last problem. Last problem is about a heat pump. It says a heat pump with a refrigerant R134A as the working fluid is used to keep a space at 25 degrees centigrade by absorbing heat from geothermal water that enters the evaporator at 50 degrees centigrade, 0.065 kgs per second, and leaves at 40 degrees centigrade. So this heat pump is essentially keeping the atmosphere at 25 degrees centigrade. And in the evaporator, what is happening? I'll zoom it out. In an evaporator, what is happening? So this is your evaporator.
करना ही है.
Sorry. So in your refrigerant R134A, it is entering at 20 degrees centigrade, and the quality of the refrigerant that is entering is 0.15, and it is leaving again at the same temperature or same pressure and as saturated vapor. So it is leaving at same temperature or same pressure as 20 degrees centigrade, same pressure. Now what is happening is that you have water that is flowing into this. Water is flowing into the system as 50 degrees centigrade, and as it comes out of the evaporator, it is at 40 degrees centigrade. So uh, essentially this water channel that is moving in and moving out of the system, it is transforming, it is giving QL or Q dot L to your refrigerant. This is what is actually taking place. Is this clear to you? There are two fluids involved. Is this clear to you? So
Yes.
Yes,
far
sir.
is it clear? All right. Now you have the first fluent as a refrigerant R134A. The first thing is you have to find, this is state 1 of refrigerant, this is state 2 of the refrigerant. Similarly, this is state 1 of water, and this is state 2 of the water. You have to find out the corresponding enthalpies. So H1 for the refrigerant R134A is essentially HF plus X HFG, and HF for a refrigerant at 20. This table below is for a refrigerant, and the above table, this table is for water. So for refrigerant which is entering at 20 degrees centigrade, the HF value is 79.32 plus 0.15 multiplied by HFG, which is 182.27. This would give me the H1 value for the refrigerant. What is it? What does this comes out to be? Have you found out the value? This is the inlet condition of the refrigerant. H2 of the refrigerant. How can you find out the H2?
2.7 kilojoule
Sorry, what?
per second.
Yes.
2.7
Sorry,
watt. 2.7
2.7.
kilojoules. 2.7 watt kilowatt.
H2 you have to find out from the table enthalpy
It-
value.
Yes, sir. Enthalpy is defined.
Enthalpy क्या है? Enthalpy is in kilowatts.
सर मैंने वो वाटर के मास फ्लो रेट में मल्टीप्लाई किया फिर.
Just focus on the refrigerant table at the moment. R134A, 20 degrees centigrade, quality 0.15. This would be the H1 value. H2 value, it is the same temperature and pressure, and it is moving out as saturated vapor. So at 20 degrees centigrade, same pressure, it is leaving out as saturated vapor. This would give you the enthalpy value of the refrigerant. Is it clear?
Yes, sir.
261.95 kilojoules per kg. So far, is it clear to you or not?
Yes, sir. Clear.
All right. The second part is for the water. Now, for water, it is entering as liquid and coming out as liquid. The first enthalpy H1 would be what?
HF plus.
HF at 50 degrees centigrade, which is
209.34.
209.
209.34 kilojoules per kg, and H2 would be
167.53.
167.53 kilojoules per kg. Now, this is known to you. The heat transfer is taking place how? I'll remove this schematic now so that we can have some space to solve the question. How's the heat transfer taking place? The mass flow of refrigerant multiplied by its enthalpy change H2 minus H1 refrigerant is essentially equal to mass flow rate of water multiplied by H2 minus H1, which is the enthalpy change of water. Now you have to find out the mass flow rate of a refrigerant. The first part is the mass flow rate of a refrigerant. This is what you have to find out. So mass flow rate of refrigerant is what? Mass flow rate of water, which is 0.065 multiplied by enthalpy difference of water, which is 167.53. There is a minus sign here. 167.53 minus
41.81.
20.34, and this would be divided by H2 minus H1 for the refrigerant, which is 261.95 minus 106.6605. That is 66. So what is the mass of a refrigerant which comes out to be?
0.000428.
Let me calculate 167.53 minus 209.34 into 0.065. This divided by 261.95 minus 106.6605. So this comes out to be 0.0175 kgs per second. This is the mass flow rate of the refrigerant. Clear? Is this clear to you?
Yes sir, clear. ठीक है.
All right. Now the second part is the rate of heat supply. Heat supply is through the condenser. This is since it's a heat pump.
सर वो साथ माइनस साइन भी
Purpose
आएगा.
of heat pump.
Mass of refrigerant.
This minus sign would essentially. This minus sign would cancel out. 167.53 minus 209. This would be a negative. This would cancel out. All right.
Oh.
All right. So the rate of heat supply. The rate of heat supply, in order to find out that, you need to find out Q dot L. Q dot L is basically the mass flow of the refrigerant, 0.0175 multiplied by its change in enthalpy, which is 261.95 minus 106.6605. So what is this value comes out to be?
2.717
kilowatts or kgs per second, kilojoules per second. Now this is known to you. So if we go to the next page, we have Q dot L is 2.71 kilowatts or 72 kilowatts. You have to find out the rate of heat supply. So you know that Q dot H is work dot net in plus Q dot L, which is work dot net in is 1.2 kilowatt plus 2.71 or 2 kilowatts, 1 kilowatt. This would essentially be 3.91 kilowatts. All right, clear?
Yes sir.
And the COP of heat pump is essentially Q dot H over work dot net in. So you have 3.91 kilowatt divided by 1.2 kilowatt. What would be the answer?
3.25.
So it's 3.25 is the answer. Clear? Is the solution clear to you?